Making an efficient hash table. Ultimately, a hash table's efficiency depends on data we're storing in the hash table. Cells are available in the hash table and hash function we're using. It makes sense why the first two factors are important. If you have a lot of data and only a few cells, there will be many collisions and the hash table will lose its efficiency. Let's say we're using a hash function that always produces a value that falls in the range from 1 to 9. An example of this is a hash function that converts letters into their corresponding numbers and keeps adding the resulting digits together until it ends up with a single digit. For example, put equals to 16 plus 21 plus 20 equals to 57. Because 57 contains more than one digit, the hash functions break up the 57 into 5 plus 7. 5 plus 7 equal to 12. 12 also contains more than one digit, so it breaks up the 12 into 1 plus 2. 1 plus 2 equal 3. In the end, put hashes into 3. This function, by its very nature, will always return a number 1 through 9. Let's return to our example hash table. With this hash function, 1 to 16, the computer would never even use cells 10 through 16, even though they exist. All data would be stuffed into cells 1 through 9. So the reason for this is that we need to allocate more cells than our expected data to make the hash table avoid collision and make it efficient. And then again, it depends on data we're storing in the hash table. Cells available in the hash table and hash function that we are using. So it's dependent on the data, kind of like the number of memory or how large the memory, and the algorithm, which is the function that we are using. It makes sense why the first two factors are important. If you have a lot of data and only a few cells, there will be many collisions and hash table will lose its efficiency. Let's say we're using a function that always produces value that falls from range 1 to 9. An example of this is a hash function that converts letters into their corresponding numbers and keeps adding the resulting digits together until it ends up with a single digit. So here we have 57, 5 plus 7 equals to 12, 1 plus 2 equals to 3. So it always makes a single digit which is less than 9. So that's the algorithm that defends largely how our function are efficient, as well as the number of allocated memory. A good hash function, therefore, is one that distributes its data across all available cells. The more we can spread out our data, the fewer collision we will have. While avoiding collision is important, we have to balance that with avoiding memory hogging as well. Although a hash table with 1000 cells for our 5 pieces of data is great for avoiding collisions, we'd be using up 1000 cells just to store just 5 pieces of data, and that's a poor use of memory. To accomplish this, computer scientists have developed the following rule of thumb. For every 7 data elements stored in a hash table, it should have 10 cells. This ratio of data to cells is called the load factor. Using this terminology, we'd say that the ideal load factor is 0.7, 7 elements over 10 cells. If you initially stored 7 pieces of data in a hash table, the computer might allocate a hash table with 10 cells. When you begin to add more data, though, the computer will expand the hash table by adding more cells and changing the hash function so that new data will be distributed evenly across the new cells. So this load factor also suggests that the algorithm and the data structure should move along with the data that's input to it. So when you begin to add more data, the computer will expand the hash table by adding more cells and changing the hash function that run on the algorithm as well. Again, most of the internals of a hash table are managed by the computer language you're using. It decides how big the hash table needs to be, what hash function to use, and when it's time to expand the hash table. So most of its internals are actually managed by the computer language you're using. It decides how big the hash table needs to be, what hash function to use, and when it comes to expand the hash table, uh, you have a right to assume that your programming language has implemented its hash table to allow for peak performance. So unlike stock and queues, which could be in array data structure under hood, this hash table is actually implemented in the or integrated in the programming language itself. So you don't need to create a program or algorithm for this data structure. It is automatically implemented under the hood. Hash tables for organization. Because a hash table keeps data in pairs, they are useful in many scenarios for organizing data. Some data exist naturally in paired form. I think, yeah. Let's see. Yeah, I thought we've discussed this. So the fast food menu and the thesaurus scenarios from this chapter are classic example of this. The menu contains each food item paired with its price. That is, the thesaurus contains each word paired with its synonym. In fact, in Python, hash tables are known as dictionaries. Since a dictionary is a common form of paired data, it's a list of words with their respective definitions. So some of the data in real world are naturally paired using hash table or key value pairs. Python, hash tables are known as dictionaries. Since a dictionary is a common form of paired data, it's a list of words with their respective definition. So Python actually called this hash table as dictionary. Other examples of naturally paired data can include tallies such as political candidates and the number of votes each receive. Like candidate A 1402021, candidate B, etc. So hash tables are such a natural fit for paired data that we can even use them to simplify conditional logic in certain instances. Say we encounter a function that returns the meaning of common HTTP status code numbers. So here, there's a conditional logic that we can convert to a hash table. So an algorithm or a conditional logic could be converted into a data structure that produces the same value, because there is a balance or kind of like a sweet spot between data structure and algorithm, because most often they are interconnected. That's why you are able to convert this conditional algorithm into a hash table data structure. So here, if we think about this code, we'll realize that the conditional logic revolves around paired data, namely the status code numbers and their respective meanings. By using a hash table, we can completely eliminate the conditional logic. So status codes equals to 200 is to OK, 301 is to move permanently, etc. Then we define status underscore meaning number and then return status code. So as you can see here, we initiate it. Instead of having this long conditional logic, we initiate a hash table data structure using status code and then multiple data key value pairs inside the array, and then before we define the function. So another common use for hash tables is to represent objects that have various attributes. For example, here's a representation of a dog: name, Fido, breed to pug, age is to 3, gender is to male. So kind of like the attributes in document relational database. I'm sorry, yeah, document non-relational, I think, is what I use in my blogging app, which has a lot of attributes in each document. So it's key value pairs. It also use hash table under the hood. As you can see, attributes are a kind of paired data, since the attribute name becomes the key and the actual attribute becomes the value. We can create an entire list of dogs if we place multiple hash tables inside an array. So here, we create a multiple hash table inside the array. So we can also put this hash table inside an array like this, where we can list the multiple attributes of different dogs. Now, hash tables for speed. So what would happen if we run some code that would convert this number, array equals 61, 30, 91, 11, 54, 38, 72, into a hash table that looks like this? So what will happen if we convert this array into a hash table? It will make our search faster, of course. So by doing a hash table lookup using 72 as the key, I can determine in one step whether the 72 is present in the hash table. The reasoning is straightforward. If 72 is a key in the hash table, I'd get back true, since the value 7 has true as its value. On the other hand, if the 72 is not a key in the hash table, I'd get back nil. So the search became O1. You either get the number as true or you get nil or null. Various languages return different values when a key is not present in a hash table. So various languages return errors in different ways. Ruby returns nil. By converting an array into a hash table in this way, we can go from ON searches to O1 searches. Here's what's interesting about using a hash table in this way. Even though hash tables are often used for naturally paired data, our data here is not paired. We just care about a list of single numbers. While we did assign a value to each key, it doesn't really matter what the value is. We use true as the value for each key, but any arbitrary value that is truthy would achieve the same results. So here, the data is not naturally paired. It's just a list, or we just want to make the searches faster. So any arbitrary value that is truthy would achieve the same result. So here is an example of making our arrays or data structure faster by using or by converting arrays into a hash table. The trick here is that by placing each number in the hash table as a key, we can later look up each of those keys in one step. If our lookup returns any value, it means the key itself must be in the hash table. If we get back nil, then the key must not be in the hash table. I refer to using a hash table in this way as using it as an index. It's my own terms. So using a hash table in this way, or converting array into a hash table, could be called using an index. So an index at the back of a book tells you whether the topic can be found in the book, instead of you having to flip through all the pages to find it. Here as well, we created the hash table to serve as kind of index. In our case, it's an index that tells us whether a specific item is contained within the original array. let's say we need to determine whether one array is a subset of another array. Take these two arrays, for example, A, B, C, D, E, F, and B, D, F. The second array, B, D, F, is a subset of the first array because every value of the second array is contained within the first array. However, if our arrays were A, B, C, D, E, F, and B, D, F, H, the second array is not subset of the first array because the second array contains the value H, which does not exist within the first array. How would we write a function that confers two arrays and let us know if one is a subset of the other? One way we can do this is using a nested loops. Essentially, we'd iterate through every element of the smaller array, and for each element in the smaller array, we then begin a second loop that iterates through each element of the larger array. If we ever find an element in the smaller array that isn't contained within the larger array, our function will return false. If the code gets past the loop, it means it never encountered a value in the smaller array that wasn't contained within the larger array, so it returns true. Here's a JavaScript implementation of this approach. Now, here's how we implement that. How do we compare the inner array so that it will return false if the element on that does not exist on its parent array? Now, function is subset. So we create a function is subset. Array1, we accept parameters array1 and array2, and then we let larger array and then let smaller array. We create a larger array and smaller array variable, or array rather. Yeah, you could say variable. Determine which array is smaller. If array1 that length is greater than array2 that length, larger array is equals to array1. Then smaller array is equals to array2. Else, if larger array is equals to array2 and smaller or else, so we're trying to determine in this conditional logic what is larger, if the input array1 or array2. Now we iterate on that iterate through smaller array. For let I equals to 0 and then I is smaller array that length less than smaller array that length, we increment on each index. Assume temporarily that the current value from the smaller array is not found in larger array. So let found match equals to false. So let's say that the current value from the smaller is not found in the larger. We initially set it to false, the found match variable. Now for each value in smaller array, iterate through it larger array. So for let j equals to 0 and then j is less than larger array that length, and then we increment. If the two values are equal, it means the current value in smaller array is present in the larger array. So for each value we found from the smaller array, we will now iterate through larger array. So we're iterating on this larger array, which is j equals to 0. Start from that index, and then as long as it's less than the array length, we increment on each index. So if the two values are equal, it means the current value in the smaller array is present in the larger array. So if smaller array I is equals to larger array j, found match equals to true. Now we will return to true. So initially we set the found match to false, because we haven't iterate on each array, smaller array yet. And then if it's true, then we break. Then if found match is equals to false, we return false. So if the current value in smaller array doesn't exist in larger array, return false. If we get to the end of the loop, it means that all values from the smaller array are present in larger array. So if we get to the end of the loop, therefore, the values from the smaller are present in the larger array, therefore, we return true. Means that it's a subset of a larger array. Otherwise, if any of the element does not match, we return false. When we analyze the efficiency of this algorithm, we find that it's O n times n, since it runs for the number of items in the first array multiplied by the number of items in the second array. Now, let's harness the power of a hash table to dramatically improve the efficiency of our algorithm. Let's ditch our original approach and start again from scratch. In our new approach, we've determined which array is larger and which is smaller. We're going to run a single loop through the larger array and store each value inside of a hash table. So first, we determine which array is larger and which is smaller by comparing it, and we're going to run only a single loop through the larger array and store each value inside of a hash table. So let hash table equals to empty. Then for earlier we let the smaller and larger array using a closed semicolon because we iterated it inside the loop and we let the user enter it. Here we created a hash table with an empty empty allocation from memory. So for const value of large array, hash table value equals to true. Now in this code snippet, we create an empty hash table inside the hash table variable. So it actually has a hash table variable. So we create an empty hash table for that. Then we iterate through each value in the larger array and add the item from the array to the hash table. So this for loop with this const value of large array are actually iterating on each value of the larger array and then putting that on that empty hash table. We add the item itself as a key and true as the value. So the item itself, which is the hash table value or the element inside of the larger array, is stored as a true as the value. For the earlier example, A, B, C, D, E, F, once we've run it through this loop, we end up with a hash table that looks like this: A true, B true, C true, D true, E true, F true. Now this becomes our index that will allow us to conduct O1 lookups of these items later on. Now here's the brilliant part. Once the first loop is complete and we now have this hash table to work with, we can then begin a second non-nested loop that iterates through the smaller array. So after that first leaf from the larger array is complete and we now have this hash table to work, we can then begin a second non-nested loop instead of that nested loop for the smaller and larger array earlier that iterates through the smaller array. So for const value again of smaller array, if not hash table value, return false. So if it's not included on the hash table value, which can be accessed using an O1 instead of ON using a regular array. Therefore, we return false. So this loop looks at each item in the smaller array and checks to see whether it exists as a key inside the hash table. Remember, the hash table stores all the items from larger array as its keys. So, if we find an item in hash table, it means that the item is also in larger array. And if we don't find an item in hash table, it means it's also not inside the larger array. So for each item in smaller array, we check whether it's a key in hash table. If it's not, that means the item isn't contained within the larger array, and the smaller array is therefore not a subset of the larger array and return false. However, if we get past this loop, it means the smaller array is a subset of the larger one. Let's put this all together into one complete function. So if we get past on that loop, so that's the next code, that function from the smaller array. If we get past that, therefore we will return true, which means that those smaller arrays is a subset of of the larger array. Now function is subset array1 array2. Let larger array semicolon, let smaller array semicolon, and then let hash table equals to empty, or let hash table equals to variable equals to empty allocation in memory. Determine which array is smaller. So if array1 that length is greater, so there's still comparison, which is larger, of course, and then is still the same on the first one, and we have a conditional if else to compare which is larger. And then these are the where's the code is different. Store all items from larger inside the hash table, which what we did earlier. For const value of large array, inside it is hash table, and then value, open close square bracket, value equals to true. Now iterate through each item in smaller array. So for const value of smaller array, if not hash table value, return false. Now if we got this far in our code without returning false, it means that all the items in the smaller array must be contained within larger array. We return true. So now how many steps this algorithm take? We iterated through each item of the larger array once in order to build the hash table. Now, how many steps this algorithm take? We iterated through each item of the larger array once in order to build the hash table. So only one. It's not nested loop, so it's not n squared. And we iterated through each item in the smaller array, taking just one step per item to look up the item in the hash table. Remember, a hash table look up takes just one step. So if we say that n is the total number of items of both arrays combined, our algorithm is ON since we touch each item just once. That is, we spent one step on each item from the larger array followed by step on each item from the smaller array. So that's a huge win over our first algorithm, which was ON times n, which could be n squared if it's the same, right? This technique of using hash table as an index comes up frequently in algorithms that require multiple searches within an array. So this algorithm of hash table are actually frequently being used for searches within an array, because again searches in array is ON while in hash table it's O1. That is, if your algorithm will need to keep searching for values inside an array, each search would itself take up to n steps. By creating a hash table index of the array, we reduce each search to only one step. So it's kind of like, instead of it being an n squared we make it an ON because a hash table is O1. So as I pointed out, what makes this technique particularly interesting is that when using a hash table as an index, we aren't even dealing with naturally paired data. Instead, we just want to know whether the key itself is in the hash table. So another thing to emphasize is that instead of it being always a key pair values, we can also use this as an index only, just so we can achieve that O1 search, so that we can make our code efficient. When instead, we just want to know whether the key itself is in the hash table. When we use the key to perform a lookup in the hash table and receive any value, no matter how arbitrary it is, it means the key must be present in the hash table. Hash tables are indispensable when it comes to building efficient software. With their O1 reads and insertions, it's difficult data structure to beat. Crafting elegant code with stocks and queues. Until now, our discussion around data structures has focused primarily on how they affect the performance of various operations. However, having a variety of data structures in your programming arsenal also allows you to create code that is simpler and easier to read. And these two data structures are not entirely new. They are just arrays with restrictions. So stocks and queues is not a new data structure, it's just an array, or rather it's an abstract data type in which a way to describe a function that restrict a certain input and produce a certain output. We will gonna discuss this further. More specifically, stocks and queues are elegant tools for handling temporary data. Like a customer's orders in a diner, it's important only until the meal is made and delivered. From operating system architecture to printing jobs to traversing data, stocks and queues serves as temporary containers that can be used to form beautiful algorithms. So these are actually data structures that if combined with algorithms could produce a beautiful algorithms. It is usually used for this word document in which is store it in memory that allow us to revert it back based on the previous deleted functions that we made or deleted data. Stocks and queues handle this kind of temporary data in memory such as this if it's not saved yet in the disk, but have a special focus on the order in which the data is handled. So it focuses on the data because like an undo function, that's a good example of this too. So a stock store data in the same way arrays do. It's simply a list of elements. The one catch is that stocks have the following three constraints. So it stores data the same way as array. So it's contiguous as well. So it's unlike hash table. So it's not a hash table. I mean, you could implement it using a hash table, but it's usually implemented using an array. So here, data can be inserted only at the end of a stock. Data can be deleted only from the end of a stock. Only the last element of a stock can be read. So what's the difference of this from the array? So these are the difference. The data can be inserted only at the end of the stock. So in array, regular classic array, you can insert it in the middle, but you need to shift away something, right? You can insert it at the beginning, but that's the worst insertion scenario. Data can be deleted only from the end. You can also delete it from the beginning, but you also need to shift it a lot. So, I mean, those operation just requires more steps because the classic array or the computer needs to fill out those empty and then, empty cell. Now, only the last element of a stock can be read. So, in classic array, you can also read, you can read all in just one step. So, there's these three operations is what makes the stocks and classic arrays different. Now, most computer science literature refers to the end of the stock as its top and the beginning of the stock as its bottom, viewing stocks as vertical arrays. So most of the literature in this view the end of its stock as its top, kind of like a plates, uh, um, a dish stock, right? A plate stock, where you can only remove the top plate. It's hard. You can technically remove the bottom first if you're gonna push that, but that's not really how it works in natural way or intuitively. So you need to remove the top plate first, so it calls as its top. The beginning of the stock or its bottom or called bottom. So viewing stocks as vertical arrays. So instead of the horizontal arrays, which are the regular arrays, looks like in literature, it is a vertical array. So the first item in the array becomes the bottom of the stock. So like the first index on that horizontal classic array becomes the bottom, and the last index becomes the top, while the last item becomes the stock stop. While the restriction of a stock seem well restrictive, we'll see shortly how they are to our benefit. Inserting a new value into a stock is called pushing onto the stock. So in literature, inserting instead of an insertion in a regular array, it's called pushing onto the stock. Think of it as adding a dish onto the top of the dish stock. Now let's push 5 onto the stock. Again, there's nothing fancy going on here. All we're really doing is just inserting a data element into the array. Now let's push 3 onto the stock. So we have here, let's put push a 0 onto the stock. Note that we're always adding data to the top. That is the end of the stock. If we wanted to insert the 0 into the bottom or middle of the stock, we couldn't, because that is the nature of a stock. So if we wanted to insert 0, we can't, because it's the fundamental structure of the stock. Last in, LIFO, last in, first out. Data can only be added to the top. Removing elements from the top of the stock is called popping from the stock. So deleting is called popping. So in regular array, it's called a deletion or removal. Here, popping from the stock. Because of a stock's restriction, we can only pop data from the top. So because of the nature of it in this array, or a way of restricting an array, we can only pop it from the top. Let's pop some elements from our example stock. First, we pop the 0. Our stock now contains only 2 elements, the 5 and the 3. Next, we pop the 3. Our stock now only contains the 5. A handy acronym used to describe stock operations is LIFO, which stands for last in, first out. All this means is that the last item pushed onto a stock is always the first item popped from it. Abstract data types. Most programming language don't actually come with stock as a built-in data type or class. So unlike hash tables and arrays, stock actually does not have a built-in syntax, you could say, that could be implemented using programming language and then could be converted to our XOR 1010-bit computer. It's actually defined function or algorithm like this, or class. So this is a stark contrast with arrays, which are available in most languages. To create a stock, then you generally have to use one of the built-in data structures to actually hold the data. So the built-in data structures like array are actually the one that you actually need to use to create this stock. Here's one way to implement a stock using a Ruby, which uses an array under the hood. So we create class stock. We define initialize. So data, we started empty and then end, and then we define push as a pushing to, or pushing a stock to the element, to the array rather. So data, and then element, and then end, and define pop. So data that pop. So we define that as a deletion, and then def read data that last. So Ruby see this data that pop as deletion, right? Because we're removing it. And notice we define these functions in a separate class stack to actually create it. And then to create it, we actually define a functions for that data structure. So as you notice, like this stock or a data structure could not be expressed using just a data structure alone. It needs to be expressed along with separate functions like this: def push, def pop, and as well as the built-in pop or deletion from Ruby. Here, read at data that last end. So last as well, it provides us the last index in Ruby, and then end. So as you can see, our stock implementation stores the data in array called at data. Whenever a stock is initialized, we automatically build an empty array with at data equals to open and close square bracket. Our stock also contains methods that push new elements to the at data array. So it contains methods, just like what we've learned in the previous video, the object-oriented programming. Pop elements from at data array and read elements from the at data array. So pop, it all does that in this data array that we initially created. So whenever we call this stock, we did this, we can call these methods, but it needs to create an array first, right? Because based on this method, the data array needs to be created first. So those, are kind of happening in the background, all at the, at the speed of light, or at the speed of your computer, right? So here, or processor rather. So our stock also contains method that push new elements to data, etc. However, by building the stock class around the array, we have built an interface that forces the user to interact with the array in limited ways. So because we build the array in a certain ways, we have forced the user to interact on it on a certain ways as well. More specifically in a restricted last in first out manner. The array is built into most programming languages and interacts directly with the computer's memory. So the array is built into most programming language and it actually interacts directly into the memory. The stock, on the other hand, is really a set of rules and processes around how we should interact with an array so that we can achieve a particular result. In fact, a stock doesn't even care about what data structure is under the hood. All it cares about is that there's a list of data elements that act in a LIFO way. So this is what I'm saying. Most often, we use array to implement it in a LIFO way, but as long as it's a list of data elements that act in a LIFO way, whether it's hash table or whether it's node, as long as it acts like that, we can call that a stock. Because of this, the stock is an example of what is known as an abstract data type. It's a kind of data structure that is a set of theoretical rules that revolve around some other built-in data structure. The sets we encountered in the previous video is also another example because some implementation of that can be a hash table. So the sets in the first video that does not allow duplicate values in the array is actually an abstract data type as well, same as this. They are simply a pieces of code that are written on top of other built-in data structures. Even if programming language does implement its own stock class, it doesn't change the fact that the stock data structure is still a concept that allows for various data structures to be used under the hood. So even if it does implement its class under the hood, it doesn't change the fact that the stock data structure is still a concept that allows for various data structures to be used under the hood. Stocks in action. Although a stock is not typically used to store data on long-term basis, it can be a great tool to handle temporary data as part of various algorithms. So though it may not be better to store the data for long-term basis, like in a disk for you to use that in your application, but it's great in memory, such as the undo functions, where you can go back to the previously deleted functions as long as the computer is still open, you haven't restarted. So let's and it can be a great tool to handle temporary data as a part of various algorithms, such as the linter, or the way we check the errors in our code is actually can be done using a stock data structures, and it's actually efficient. Now let's create the beginnings of a JavaScript linter. That is a program that inspects a programmer's JavaScript code and ensures that each line is syntactically correct. It can be very complicated to create a linter, as there are many different aspects of syntax to inspect. We'll focus on just one specific aspect of the linter: opening and closing braces. This include parentheses, square brackets, and curly braces, all common causes of frustrating syntax error. So again, we're gonna focus on parentheses, square brackets, and curly braces. To solve this problem, let's first analyze what type of syntax is incorrect when it comes to braces. So these three, parentheses, square brackets, and curly braces, are all the same category of braces. Now, to be able to create an algorithm using this LIFO data structure, we need to create a pseudocode first, or the things that we want to be true and not true during the steps of the algorithm that we're gonna instruct the computer. Now, if we break it down, we'll find that there are three situations of erroneous syntax. Here, the first is when there is an opening brace that doesn't have a corresponding closing brace, which will cause syntax error type number 1, such as this. Opening parenthesis var x equals to closing semicolon. Now, the second is when there is a closing brace that was never preceded by a corresponding opening brace, which will call that syntax error type 2, var x equals to 2. So like here, var x equals to 2, semicolon, closing parenthesis. So as you can see, we prepare the algorithm to handle these edge cases, in which we want our algorithm to work along with the data structure, which are LIFO structure. So those are the things that we need to hit, or the requirements we need to achieve. Now, we're just trying to create all the edge cases, kind of like a pseudocode. It's not a pseudocode yet, but we're just trying to make it, understand the problem in a high level. Kind of like in design, you're trying to list contextual requirements or key paths from the customers. So here, the third will refer to as syntax error type number 3, is when a closing brace is not the same type of brace as the immediately preceding opening brace, such as an opening parenthesis and open square bracket opening square bracket and closing parenthesis. So this is where stock allow us to implement a beautiful linting algorithm. We prepare an empty stock and then we read each character from left to the to right following these rules. So first we prepare an empty stock and then of course we read each character from left to right following these rules. If we find any character, so this is the pseudocode, if we find any character that isn't a type of brace, parenthesis, square bracket, or curly brace, we ignore it and move on. If we find an opening brace, we push it onto the stock. Having it on the stock means we're waiting to close that particular brace. If we find a closing brace, we pop the top element in the stock and inspect it. We then analyze. So as you can see, the key thing in the stock is that we're just determining if it's a opening or closing brace. We can easily determine that by defining the brace, right? Or what is the brace we're looking for inside the characters in the code, the strings or numbers, whatever data we have on the code. Now we then analyze. So how do we analyze within the brace characters? If the item we pop, which is always an opening brace, does not match the closing brace, so if it's not equal or does not match based on the brace equality that we'll later define in JavaScript, it means we've encountered syntax error number 3. So let's say we have the opening and closing, opening parenthesis and closing square bracket. If you couldn't pop an element because the stock was empty, that means the current closing brace doesn't have a corresponding opening brace beforehand. This is syntax error type number 2. As you can see, the algorithm may not be able to determine or if it's an opening or closing brace, but if we determine that the stock was empty, like we couldn't pop it means that the current closing brace doesn't have a corresponding opening, which means that the when we are entering it in the stock, we actually don't know if it's an opening or closing. The only time we know is if we don't we're not able to pop another element from the stock. So if the item we pop is a corresponding match for the closing brace, it means we've successfully closed the opening brace. So based on the functions we defined, which we will later see, if it match on that, if it's equal, we can continue parsing the line of JavaScript code until we reach the end. So we're gonna run a loop to do that on all the characters in the code. Now if you want to make it to the end of the line and there's still something left on the stock, that means there's an opening brace without a corresponding closing brace, which is a syntax number 1. So if you make it to the end of the line and there's still left on the stock, it means that there's an opening brace without a corresponding closing brace, which is a syntax. So there's another edge cases here. So we have this case like when all is true, we're gonna close the loop. But here there's another type in which there is when we get to the end of the loop and then there's still something left on the stock, it's not empty, it means that there's an opening brace without a closing brace. So that's another error as well, syntax error type number 1. Just a moment guys, I'll just take my coffee. Alright, so let's see this in action using the following example. So here we have um, uh, opening parenthesis var x equals to opening curly brace y colon opening square bracket 1 comma 2 comma 3 closing square bracket closing curly brace and then closing parenthesis. So after we prepare an empty stock, we begin reading each character from left to right. So we prepare the empty stock first on that code. So if we're gonna apply that code in these characters, first we're gonna prepare an empty stock, and then we will gonna put that this brace first, the first parenthesis on that stock. So after we prepare an empty stock, we begin reading each character from left to right. Step 1, we begin with the first character, which happens to be an opening parenthesis, and then var, we ignore it. Since it's a type of opening brace, we push it onto the stock, so the opening parenthesis. We then ignore all the characters var x equals since they aren't brace characters. Step 3, we encounter our next opening brace, which is the curly brace. We push it on the stock. Step 4. So as you can see, the encounter ring is actually a step. So step 2, since it's an opening brace, we push it. First, we begin the first character, which happens to be an opening stop. So the recognition of the brace is a step as well. And then we then ignore the y and then the colon. Step 5, we encounter again the opening square bracket. And then step 6, we add that to the stock as well, or we push it. We then ignore 1, comma 2, comma 3. Step 7, we encounter our first closing brace, a closing square bracket. So encountering again step 8, we pop the element at the top of the stock because that's a closing brace, which happens to be an opening square bracket. So once we find a closing brace, we're gonna pop something on the stock to close that opening brace, closing brace rather. Since our closing bracket is a corresponding match to the top elements of the stock, it means we can continue with our algorithm without throwing any errors. We move on, encountering a closing curly bracket again. Then we pop the top item from the stock. It's an opening curly brace, so we found a match with the current closing brace. Step 11, we encounter a closing parenthesis. We pop that element in the stock. It's a corresponding match, so there are no errors so far. So here's a Ruby implementation of the preceding algorithm. So we create a class called linter, and then we define initialize. So again, there's no built-in data structure, though some programming language built a LIFO. But in this case, we include a LIFO with this linter. So we're gonna actually create this. But usually, we don't implement it in most current or modern programming because it's usually implemented using the Node.js API. So here, we're just gonna create a simple linter algorithm. Class linter, name linter, def initialize, and then we use a simple array to serve as our stock. So we use an array as our data structure for this LIFO stock. So as stock equals to stock.new. So notice this stock is actually the stock that we create earlier, and then we end, and then we define lint. So as you can see, our algorithm works like this. First, we create a stock which we imported from the stock we created earlier, and then this is where we create the lint. So the name of the class as a whole is linter, but this method or function is called lint, and it accepts text as parameter. Now we start a loop which read each character in our text. So text that each underscore char do, and then the character. If the character is an opening brace, if is underscore opening underscore brace question mark is char, we push it onto the stock at stock dot push, which is a parameter char. If the character is closing brace, else if is underscore closing underscore brace question car pop from the stock pop underscore opening underscore brace equals to at stock dot pop. So if not pop underscore opening underscore brace return char doesn't have an opening brace and so this if are inside the closing brace else if so and then we end and then we create another if conditional statement if the pop opening brace doesn't match the current closing brace we produce an error if is underscore not underscore a match pop underscore opening underscore brace comma char then we return char has mismatch opening brace then we end so if we get to the end of the line and the stock isn't empty if at stock dot read it means so we create a if at stock dot read after that logic it means we have an opening brace without a corresponding closing brace so we produce an error return at stock dot read does not have a closing brace and then after that we have logic return true if line has no response so return true and then private which can only be accessed through private so here's where we define the opening brace and the closing brace so def is underscore opening underscore brace we accept char and then inside this we have opening parenthesis quote comma opening square bracket quote comma opening curly bracket quote and then closing square bracket that include question accept char and then end and after that we define the is underscore closing underscore brace question which accept char opening square bracket quote open closing parenthesis so these are the closing braces comma quote closing square bracket comma closing curly braces closing square bracket that include question char end and lastly we define is underscore not underscore a underscore match which has opening underscore brace and then closing underscore brace as its input so this is actually the one determining if it match so closing underscore brace is not equals to opening curly brace quote opening parenthesis to closing parenthesis quote comma opening square bracket to closing square bracket comma opening curly to opening closing curly bracket and then opening brace underscore brace as an input and then end so what this method do so the lint method accept a string containing a JavaScript code and iterates over each characters with text that each underscore char do char so or parameter char so this character is actually accepting a JavaScript code so this is actually how we check or like compare the values of that algorithm. Now if we encounter an opening brace we push it onto the stock if is underscore opening brace or the char that we enter from JavaScript code we push that on that empty stock at stock that push char note that we're using a helper method defined as follows called is underscore opening underscore brace question which checks whether the character is an opening brace such as quote square bracket quote opening parenthesis the one that we defined earlier so when we encounter a closing brace we pop the top of the stock and store it in a variable called pop underscore opening underscore brace so pop underscore opening underscore brace equals to at stock dot pop which we defined in the class stock earlier so our stock only stores opening braces so whatever we pop will be some sort of opening brace assuming there was something on the stock to pop however it's possible to the stock was empty so again our stock only stores opening braces So whatever we pop will be some sort of opening braces. So basically, this stock only stores opening brace. So whatever we pop from the stock is actually an opening brace, assuming there was something on the stock to pop, because that opening brace will eventually close the closing brace. However, it's possible the stock was empty, in which case the result of our pop will be nil. Sorry about that, I took coffee. So, however, it's possible the stock was empty. So, in which case, the result of our pop will be null, since there's no opening bracket. If this is the case, it means we've encountered syntax error type number 1. So, here's the logic for that, conditional logic. If not, or if exclamation pop underscore opening underscore brace return. So if it's not an opening brace, car doesn't have an opening brace. So this is what the code means. And then end. For simplicity's sake, we return a basic string containing an error message when we encounter any errors during our linting process. So we're just using a basic string, assuming that we did our basic string data type of data instead of like complicated and producing any like a chat GPT way of determining what's the error, right? So assuming that we did pop an opening brace of the stock, we then check it to see whether it matches the current closing brace. So assuming that we're able to pop an opening brace, if it doesn't match, this is syntax error type number 3. So if is underscore not underscore a underscore match, then the pop underscore opening underscore brace comma char return char has mismatch opening brace, and then end. So this is underscore not underscore a underscore match helper method is defined later in our code. Finally, when our code finishes parsing the line, so this is underscore not match is actually defined on the last part of the code, which is here, which define if the opening and then closing braces. So this actually the code or the if else logic that determine if it doesn't match, so has mismatch opening brace. So that's how the code determines if that brace it's not actually less than or equal, you know, we define that as a opening and closing brace. And then if pop underscore opening underscore brace and then char only, we return a mismatch opening brace, kind of like if it's not much on that opening and closing brace. So finally, when our code finishes parsing the line, we check whether there are any opening braces left in the stock with at stock.read. If there are, it means we have an opening brace that was never closed, and we produce an error message. This is a syntax error type number 1. So if at stock.read return stock.read does not have a closing brace. So if we did not close that loop, therefore we will read that and we're able to read that, it means that it doesn't have a closing brace. So finally, we return true if the JavaScript contains no errors. We can then use our linter class as follows. Linter equals to linter.new puts linter.lint. So when we input it, so this is how we print that or use this algorithm. We create linter equals to linter.new, so we create a new class of that, and then puts linter.lint. So linter.lint, which is the method inside of this class. So we input these characters. In this example, the JavaScript code is correct, so we just get back true. However, if we input a line that has an error, such as missing opening parentheses, we'll get error message doesn't have opening brace. So this is how this algorithm works, which is amazing. to really understand how it works in detail. So in this example, we use a stock to implement our linter with a really neat algorithm. But if a stock actually uses an array under the hood, why bother with the stock? Couldn't we have accomplished the same task using an array? So this is where the importance of constrained data structure comes. So first, when we work with a constrained data structure, we can prevent potential bugs because we're not accepting this incorrect data or inaccurate data such as this. It being used in code before deployments, so that we know what is the part of the code that has a potential bug. So the linting algorithm, for example, only works if we exclusively remove items from the top of the stock. So it only works if we remove it from the top of the stock. If we actually made the step, of popping or encountering and then closing the curly brackets. Now, if a programmer inadvertently writes code that removes items from the middle of the array, the algorithm will break down. So if the programmer actually remove a stock at the middle, the algorithm will break down. By using a stock, we're forced into only removing items from the top, as it's impossible to get the stock to remove any other item. Second, data structures like stock give us a new mental model for tackling problems. The stock, for example, give us the whole idea of a last in, first out process. We can then apply this LIFO mindset to solve all sorts of problems such as the linter just described. And once we're familiar with stock and its LIFO nature, the code we write using the stock becomes familiar. And once we're familiar with the stock and its LIFO nature, the code we write using the stock becomes familiar and elegant to other developers who read our code. So if we're familiar with this code, therefore we can better write and express our code to other developer, and then it becomes familiar and elegant because they just know that it's a LIFO. As soon as someone sees a stock being used within an algorithm, they immediately know that the algorithm is working with a LIFO based process. So it's kind of like a persona in design. It's a great communication tool to other stakeholders, so in this case developers. Stocks are ideal for processing any data that should be handled last in, first out. The undo function is in a word processor, for example, is a great use case for a stock. As the user types, we keep track of each keystroke by pushing the keystroke onto the stock. So that's how actually we keep track of each the keyboard strokes that we put on the memory. We put that inside the stock of the LIFO algorithm. So then, when the user hits the undo key or Control Z, we pop the most recent keystroke from the stock and eliminate it from the document. So in this case, we pop the previous version of the command that we put, so and eliminate it from the document. So at this point, the next to most recent keystroke is now sitting at the top of the stock, ready to be undone if need be. So queues. A queues is another data structure designed to process temporary data. Just a moment, I just take my coffee. It's like a stock in many ways, except that it processes data in a different order. So it's a first in, first out, kind of like in a movie. So you can think of a queue as a line of people at the movie theater. The first one in the line is the first one to leave the line. Just a moment, guys. There you go. With queues, the first item added to the queue is the first item to be removed. As with a line of people, a queue is usually depicted horizontally. It's also common to refer to the beginning of the queue as its front and the end of the queue as its back. So the first, it's a horizontal queue. It's the best way to express that. And the first is called front, and the end of the queue is called its back. Like stocks, queues are arrays mostly, but it can be implemented in other data structures with three different restrictions. It's just a different set of restrictions. So data can be inserted only at the end of a queue. So this is the identical behavior to the stock. Data can be deleted only from the front of a queue. So it can be only added at first. This is the opposite behavior of the stock. Only the element at the front of a queue can be read. This too is the opposite of the stock. So it's the same when it comes to insertion, but deletion and reading is opposite. So just a moment. Why is that? Oh my god. Did I change it? No, I didn't. So yeah, first let's see a queue in action, beginning with an empty queue. First, we insert a find. A common term for inserting into a queue is enqueue. So inserting instead of push in stock, it's enqueue in queues, enqueue. But we'll use the terms insert and enqueue interchangeably. So 5. Next, we insert a 9. So as you can see, it's a horizontal array. Next, we insert 100. So as of now, the queue has functioned just like a stock. However, removing data happens in the reverse. As we remove data from the front of the queue, removing an element from a queue is also known as the queuing. So instead of popping, it's called the queuing, and it's actually happening at the front instead, or at the bottom if it's a stock. If we want to remove data, we must start with the 5 since it's at the front of the queue. Next, we remove the 9. Our queue now only contains one element, the 100. Again, our queue class wraps the array with an interface that restricts our interaction with the data. So again, our queue class wraps the array with an interface that restricts our interaction with the data, just like the stock, but it's a different kind of restriction, only allowing us to process the data in specific ways. The enqueue method allows us to insert data at the end of the array. The enqueue, or insertion or pushing, allows us to insert data at the end of the array. It's like the same with the stock. Well, the queue removes the first item from the array, or the from the bottom actually, if we're talking about stock. And the read method allows us to pick at just the very first element of the array. So we can read the first or the bottom of the stock in this case, but it's called what do you call this? It's still reading, but for delete for inserting it's called enqueue, and for deleting it's called the queue. And the read method allows to pick just at the very first element of the array. Here's a Ruby implementation of a queue. So here, class queue. So you define initialize, and then add data is an empty array, and then end, and then we define enqueue element. It's kind of like the the stock that we created earlier without the read algorithm. So add data element, because insertion or enqueue is allowed at the end of the index as well, and then end, and then def the queue. So the Ruby shift method removes and returns the first element of an array. So for stock, it's actually pop. With the Ruby define it as pop, but here for since it's also the pop also removed the last index in the array, here we use shift to delete it, and it's also actually applied at the first element or first index of the array, and then end, and then def read and add data that first instead of add data that last in stock, and then end. So queues in action. So queues are common in many applications, ranging from printing jobs to background workers in web applications. Let's say we were programming a simple Ruby interface for a printer that can accept printing jobs from various computers across a network. We want to make sure we print each document in the order in which they were received. This code uses a Ruby implementation of queue class from earlier. So again, just like in stock, we create a stock LIFO structure. Now here we created the queue FIFA structure before we create the algorithm. In this case, in the last case, we create a lint algorithm. Now here we create a print manager algorithm, which handles print jobs from multiple networks. So we create a class print manager, then we initialize a queue. Def initialize at queue equals to queue.new. So we create an empty queue array, and then def queue underscore print underscore job document at queue.enqueue document, and then end. So as you can see, we have we use the enqueue for adding or inserting at the end, and then def we define a run method. Each time this loop runs, we leave the document at the front of the queue. So we read this the one that we enqueue here. While at queue that read, we dequeue the document and print it. Print at the queue that the queue, and then end. And so we so yeah, we use a while loop inside the run, and then we print queue at the queue. So end, and then private, we define print the document. Code to run the actual printer goes here. For demo purposes, we'll print to the terminal, puts document, and then end. So we can then utilize this class as follow. Print underscore manager equals to print manager.u. We create that, and then we create a queue underscore print job. So we queue the first document first, and then second, and then third, so that this will be the first document to be print, and then we define the run. So this run will loop on this three queue underscore print job. So this is the while at queue.read print queue.dequeue means, because remember, dequeuing is removing things that we already read. So each time we call queue underscore print underscore job, we add the document represented by a string, in this example to the queue. So here we add the document using queue underscore print underscore job method. We enqueue that, and then we when we call run, we print each document by processing them in the order in which they receive. So def run while at queue read print at queue.dequeue. So again, the queue, we can only dequeue or read from the front or in the stock, right? Dequeuing or deleting can only happen from the first index in the array, and then end. So note how the queue each document as we print it. When we run the previous code, the program will output the three documents in the same order in which they were received. So while this example is simplified and abstracts away some of the nitty-gritty details that a real live printing system may have to deal with, the fundamental use of queue for such an application is very real and serves as the foundation for building such system. Queues are also the perfect tool for handling asynchronous requests. So asynchronous requests, they ensure that requests are processed in the order in which they were received. Asynchronous is actually how Node.js or JavaScript server works. That's how they were able to create dynamic web applications today, or and the operating system as well, how they were able to handle multiple requests or multiple application at the same time, because they handled this asynchronously. So this is actually the underlying data structures that can be used for that, and most likely has been are being used for those kind of tasks. So they are also commonly used to model real-world scenarios where events need to occur in certain order, such as airplanes waiting for takeoff and patients waiting for their doctor. We can now learn recursion, which depends upon a stack. So recursion recursively recurs with recursion. So recursion is basically calling the same function inside the function, which calls it indefinitely. So in this case, the way there is of course a memory limit for this, or there is a memory downsides, because if you call the same functions multiple times, then the memory will just crash, right? But there's a way for us to counteract that disadvantage, as we will discuss here. So recursion is the term for a function calling itself. When harnessed correctly, though, recursion can be a powerful tool. So function blah is example in JavaScript, and then we call blah inside it. So recurs instead of loop. So actually, whenever we have loop, we can actually use recursion instead. So here's an example. Let's say you work at NASA and need to program a countdown function for launching spacecraft. The particular function that you're asked to write should accept a number, such as 10, and display the numbers from 10 to 0. Odds are that you wrote a simple loop along the lines of this JavaScript implementation, like function countdown, and accept a number, and then for let I equals the number, and then I is greater than equals to 0, I decrement or minus, and then console.log I. So that's the normal loop implementation. There's nothing wrong with this implementation, but it may never occurred to you that you don't have to use a loop. How? Let's try recursion instead. Here's the first attempt at using recursion to implement our countdown function. Function countdown parameter number, then console.log number, then semicolon, and then countdown parameters number minus 1. So let's walk through this code step by step. We call countdown 10. So the argument variable number start out as 10. Step 2. So again, step 1 we call countdown 10. So that's the first step. So the argument variable number starts out as 10. So this is the recursive implementation of that loop. Step 2, we print number which contains the value 10 to the console. Step 3, before the countdown function is complete, it calls countdown 9 since number minus 1 is 9. Step 4, countdown 9 begins running. In it, we print the number which is currently 9 to the console. Step 5, before countdown 9 is complete, it calls countdown 8. So as you can see, it's there is a simultaneous computation that's being done, while the previous computation are still being calculated. That's the essence of this recursion, right? You're calling the function itself, your own function itself. So before countdown 9 is complete, which is step 5, it calls countdown 8. Step 6, countdown 8 begins running. We print 8 to the console. So before we continue stepping through the code, note how we're using recursion to achieve our goal. We're not using any loop constructs, but by simply having the countdown function call itself, we were able to count down from 10 and print each number to the console. In almost any case in which you can use a loop, you can also use recursion. Now the base case, this is actually how we resolve that infinite loop. So how can we stop that at a certain point, just so we can achieve just what we have achieved in the loop? So let's continue our walkthrough of the countdown function. We'll skip a few steps per brevity. Step 21, we call countdown 0. Step 22, we print a number that is 0 to the console. Step 23, we call countdown -1. As you can see, in that 10 input parameter, we're now on step 21. So it means that we're essentially having 2 steps in each of the number. So here, step 23, we call countdown -1. Step 24, we print number that is -1 to the console. As you can see, our solution is not perfect as we'll end up infinitely printing negative numbers. To perfect our solution, we need a way to end our countdown at 0 and prevent the recursion from continuing on forever. We can solve this problem by adding a conditional statement that ensures that if number is currently 0, we don't call countdown, open and close parentheses again. So here, function countdown accept a number, console.log number. If number is equal 0, return, so close the loop, else countdown number -1. So in recursion terminology, the case which our function will not recur is known as the base case. So 0 is the base case for our countdown function. Again, every recursive function needs at least one base case to prevent it from calling itself. So it should have a base case. Okay. Reading recursive code. So we'll do this by looking at another example, calculating factorial. So a factorial is best illustrated with some examples. So here, the factorial of 3 is 3 times 2 times 1 equals to 6. The factorial of 5 is 5 times 4 times 3 times 2 times 1 equals 120. And so on and so forth. So here's a recursive implementation that returns a number factorial using RuV. With def factorial, accept number. If number equals to 1, return 1. Else, return number times factorial number -1. So as you can see, we have a base case 1. And then in this if-else logic, we return a number times factorial number -1, and then we have 2n. So this code can look somewhat confusing at first glance. To walk through the code to see what it does, here's the process I recommend. First, identify the base case. 2, walk through the function for the base case. Third, identify the next to last case. This is the case just before the base case, as I'll demonstrate momentarily. So next to last case, this is actually the case just before the base case, which we're gonna discuss further for us to be able to explain or distinguish that on that where that compute happens inside the computer. And walk through the walk through the function for the next to last case. Fifth, repeat this process by identifying the case before the one you just analyzed and walk through the function for that case. Now let's apply this process to the preceding code. So again, fifth is repeat the process by identifying the case before the one you just analyze, which is the next to last case, and the or the the case just before the best case. And then you need to repeat that process by identifying the case before the one you just analyzed or the next to last case, and walk through the function for that case. So let's apply this. It's kind of like this, number times factorial number -1, because it's the case next to the last case. So here, let's apply this process to the preceding code. If we analyze the code, we'll quickly notice that there are two paths. If number equals to 1, we return 1. Else, return number times factorial number -1. We can see that the recursion happens here as factorial calls itself. Else, return number times factorial number -1. So it must be that the following code refers to the base case, since this is the case in which the function does not call except if number equals to 1 and return 1. So the base case is actually the case in which the function does not call itself. That's why it's a base case. It's where we stop that infinite calling. So we can conclude then that number being 1 is the base case. Next, let's walk through the factorial method, assuming it's dealing with the base case, which would be factorial 1. Again, the relevant code from our method is if number equals to 1, return 1. Well, that's pretty simple. It's the base case, so no recursions actually happens. If we call factorial 1, the method simply returns 1. Okay, so grab a napkin and write this fact down. Factorial 1 returns 1. Next, let's move on to the next case, which would be factorial 2. The relevant line of code from our method is else return number times factorial number minus 1 and then end. So calling our factorial 2 will return 2 times factorial 1. To calculate 2 times factorial 1, we need to know what factorial 1 returns. If you check your napkin, you'll see that it returns 1. So 2 times factorial 1 will return 2 times 1, which just happened to be 2. Add this fact to your napkin. Factorial 2 returns 2, factorial 1 returns 1. Now, what happens if we call factorial 3? Again, the relevant line of code is else return number times factorial number minus 1 end. So, that would translate into number 3 times factorial 2. What does factorial 2 return? You don't have to figure that out all over again. Since it's on your napkin, it returns 2. So factorial 3 will return 6 because 3 times 2 equals to 6. Go ahead and add this wonderful factor to your napkin. Factorial 3 returns 6. Factorial 2 returns 2. Factorial 1 returns 1. As you can see, starting the analysis from the base case and building up is a great way to reason about recursive code. So recursion in the eyes of computer, it's one thing for humans to reason about recursion using the earlier napkin method. However, the computer has to do the tricky work of calling a function from within the function itself. So let's break down the process of how the computer executes a recursive function. Say that we call factorial 3. Since 3 isn't the best case, the computer reaches the line which launches the function factorial 2. Return number times factorial number minus 1. But there's a catch. When a computer begins to run factorial 2, did the computer yet complete running factorial 3? This is what makes recursion tricky for the computer. Until the computer reaches the end keyword of factorial 3, it's not done with factorial 3. So we enter into a weird situation. The computer did not yet complete executing factorial 3, yet it's starting to run factorial 2. So it's not done with computing the 3, but it's now running to starting running factorial 2 while still in the middle of factorial 3. And factorial 2 isn't the end of the story because factorial 2 triggers factorial 1. So it starts running the 1 while it's still computing factorial 2. So it's a pretty crazy thing while it's still in the middle of running factorial 3. So as you can see, you have 3, 2, 1 simultaneously calculating. The computer calls factorial 2. And while running factorial 2, the computer runs factorial 1. It turns out that factorial 1 runs in the middle of both factorial 2 and 3. So how does the computer keep track all of this, of that 3 calculation? It needs some way to remember that after it finishes factorial 1, it needs to go back and finish running factorial 2. So it needs some way to remember that after it finished the factorial 1, it needs to go back and finish running factorial 2. And then it needs to remember to complete factorial 3 once it completed factorial 2. So here's where the stuck will come. So the knowledge of tuck. The computer begins by calling factorial 3 before the method completes executing. Sorry. The computer begins by calling factorial 3 and then before the method completes executing, however, factorial 2 gets called. In order to track that the computer is still in the middle of factorial 3, the computer pushes that information onto a call stack. So here, factorial 3. This indicates that the computer is in the middle of factorial 3. Really, the computer also needs to say which line it's in the middle of, and some things like variable values, but I'm keeping the diagram simple. So the computer then proceeds to execute factorial 2. So it puts that on the stack. Now factorial 2 in turn calls factorial 1. Before the computer dives into factorial 1 though, the computer needs to remember that it's still in the middle of factorial 2. So it pushes that into the stack as well. The computer then executes factorial 1. Since 1 is the base case, factorial 1 completes without calling the factorial method. So the computer then executes factorial 1. Since 1 is the best case, factorial 1 completes without calling the factorial method again. So it stops on the factorial 1 because that's where the loop ends. After the recursive function ends. So after the computer completes factorial 1, it checks the call stack to see whether it's in the middle of any other functions. So if there's something in the call stacks, such as this factorial 2 and 3, it means that the computer still has work to do, namely wrap up some other functions it was in the middle of. If you recall, stacks are restricted in that we can only pop its top element. So this is actually how recursive works in the eyes of computers. So this ideal for recursion, since the top element will be the most recently called function, which is what the computer needs to wrap up next. It's a LIFO situation. So it's not a FIFO, which is a queue. The function that was called last, that is most recently, is the function we need to complete first. So the next thing the computer does is pop the top element of the call stack, which is currently is factorial 2. Now the computer then completes its execution of factorial 2. Now the computer pops the next item from the stack. By this time, only factorial 3 is left on the stack. As you can see, after the 1, it needs to calculate the 2 first before the 3. So the computer pops it and therefore completes running factorial 3. So as you can see, since we compute it next from the base case, which is the factorial 2, it executes that first before it executes that in the factorial 3 in the stack. But it actually begins executing the factorial 3 well, it's executing the factorial 2, just like the stack we've seen earlier. So at this point, the stack is empty, so the computer knows it's done executing all of the methods and the recursion is complete. So at this point, the stack is empty. So the computer knows it's done executing of all the methods and the recursion is complete. Looking back at this example from a bird's eye view, you'll see that the order in which the computer calculates the factorial of 3 is as follows. Factorial 3 is called first. Before it's done, factorial 2 is called second. Before it's done, factorial 1 is called third. And again, since that's the end of the stack, the factorial 1 is completed first, factorial 2 is completed based on the result of factorial 1. Again, that's the base case and this is the next base case. And then this will be the basis of this factorial 3. Finally, factorial 3 is completed based on the result of factorial 2. The factorial function is calculation made based on recursion. The calculation is ultimately made by factorial 1, passing its result, which is 1, to factorial 2. Then factorial 2 multiplies this 1 by 2, yielding 2, and passes this result to factorial 3. Finally, factorial 3 takes this result and multiplies it by 3, computing the result of 6. Some refer to this idea of passing value up through the call stack. That is, each recursive function returns its computed value to its parent function. So kind of like the computed value of 1 return to its parent value 2, so that 2 can use that and then this 2, which is has a parent 3, can return that as its child result of the factorial. So eventually that the function that was initially called first computes the final value. Now stack overflow. So this is where the memory got overflow because of this infinite calling of this recursive function. Now let's take a look back at infinite recursion. So if you notice, stack overflow really came from the stack data structure, right? Because the stack just keep inserting or pushing element without actually popping out. So let's take a look back at the infinite recursion example from the beginning of the chapter. Recall that blah called itself an ad infinitum. What do you think will happen to the call stack? In the case of infinite recursion, the computer keeps pushing the same function again and again onto the call stack. The call stack grows and grows until eventually the computer reaches a point where there's simply no more room in its short-term memory to hold all this data. This causes an error known as stack overflow. The computer just shuts down the recursion and says, I refuse to call the function again because I'm running out of memory. So the memory are designed to break that loop, so that will cause an error to your app. Now, file system traversal. Let's say you have a script. I will continue this with this in the next video. But file system traversal is just traversing inside the subdirectories of your directory folder. So let's say you have a folder and you want to know all the subfolders. Let's say you have a nested subfolders, and that therefore you're gonna use this. You can use a recursive function and use a base case to stop when you reach the bottom. So again guys, thank you for watching. See you on the next video.